Okay, in this lecture we are going to learn how to calculate projectiles that are at an angle. In the last lecture we learned about horizontal projectiles, so we had no vertical component to our velocity, so a projectile that looked kind of like this. Okay, and it flew off the hill and then lands on the ground somewhere. So in this video, we're going to have a projectile that's launched at an angle, and we're going to start with a projectile that's launched at an angle from the ground. Okay, so let's say I have, here's the ground, and I have a little cannon, and I'm going to launch the projectile at 45 degrees. Okay, and we'll say that it leaves at 10 meters per second. All right. Now, in this type of problem, it is just like the other problem in that time is linked between both the x and the y component. Okay. Last time we had an issue with the fact that the y component was 0, so that was pretty easy for us. We didn't have to calculate anything. We just treated it like a dropping problem. Okay. But in this case, we have some y component to our projectile, right, which would be this, which we can very easily calculate, right? So this is just the y component of this vector. So I would use sine because it's the opposite. And so the sine of 45 times 10 will give me what the component of that vector is. So let's just do that really quick. And I get at 7.1 meters per second. Okay, so this is the y component. Now we're going to treat this like it's a problem where I've thrown something straight up in the air. Okay, so I have the y component. We're going to use the y component when we're dealing with gravity because gravity works in the y direction. Okay, so let's just calculate how long the ball is in the air if I launch it at a 45-degree angle at 10 meters per second. And we should know that this is pretty easy, right? Because just like we're tossing a ball up, I should just be able to look at the initial velocity and calculate this. So remember up here, sort of where it's at its maximum arc, the v final is going to be 0 meters per second. Okay? So I know just by looking at this that t equals 1.42 seconds. But let me just remind you how we did that, okay? Remember that acceleration is equal to v final minus v initial all over t. And we're going to solve for t, so I'll multiply by t on both sides. Okay, and it'll cancel. And then I will divide by a. So I end up with t being equal to v final minus v initial all over a. Okay? Or saying that my 0 meters per second minus my 7.1 meters per second all over a negative 10. That'll give me 0.71 seconds. Well, that's the time to go up, and we want the time up and down, so that's where I get my 1.42 from. Right, t total. Okay? So if I want to know then how far away does this projectile land, okay, I'm asked to calculate this, right? Well, what is that? That's actually my displacement in the x direction. So now I'm dealing with x's, but I know that my time should be the same for both, okay? So if I look and I see if I launch something up at an angle, okay, it's going to have an x component of velocity right here, okay? Now because I use 45 degrees, it makes it really easy because the sine and cosine of 45 are exactly the same. So all I have to do is rewrite that. Now I've got the cosine of 45 times 10. And I know that in the x direction, I have an initial x velocity of 7.1 meters per second. Okay. Now just like in the horizontal projectile problems, the x direction doesn't have any sort of acceleration if we ignore wind resistance. Acceleration is only occurring in the y direction. So we can assume that it has a constant velocity in the x direction the entire time. Okay? So then all we need to do is take our vx equal to dx over t. Okay? Time is the same. Velocity I just calculated in the x direction. And d is what I'm trying to solve for. So if I just take vx times t, it'll give me dx. Okay? Which would be 7.1 times 1.42, which is 10.08 meters. Okay, so that should solve every single part of this equation. I know time in the air, I know a displacement in the x direction. Okay, now if I wanted to solve maybe for the height, okay, let's say displacement in the y direction. Okay, this is a y direction, so we're going to deal with the y components. This is just like a problem where we're tossing something up in the air. Okay, let me go to the next page so you can see this. Okay, so we're just going to imagine that we're tossing something up in the air, but this is my initial y velocity. So I have velocity initial y equal to 7.1. I know my final velocity up there is 0. Okay, I know my acceleration is negative 10 meters per second squared. So just using this information, I should be able to solve for d. Okay, so I can take bf squared equals v initial squared plus 2ad. Okay, now I could also treat it like a dropping problem, and then I could use d equals v initial t plus 1/2 at squared. Let's do it this way because it'll be a little bit easier, right? I know the time is 0.71 seconds. Okay, so this term will cancel out because now my v initial is at the top and my v final is at the bottom. So I get d is equal to 1/2 of negative 10 times 0.71 squared. Okay, either way I do it, I should get exactly the same answer. 0.5 times 10 times 0.71 squared. It's going to be 2.52 meters. So my displacement in the y direction is 2.52 meters. Okay. Now one last thing I want to point out in this video is that 45 degrees is the maximum angle at which you can launch something, and I'm just going to draw a picture. Okay. So if I were to want to max my distance and see how far could this thing actually shoot, whatever I'm launching it out of, a 45 degree angle, okay, will give me the maximum displacement in the x direction. It'll get my projectile the furthest away at 45 degrees. Okay. What ends up happening is if I shoot it lower, I have more of a y, or I have more of an x component, but because I'm not shooting up as much, the t is going to be shorter, right? It'll take less time for it to hit the ground. If I were to increase the angle, now I'm launching more up in the y direction, making the time longer, so it'll take longer to fly up and come back down, but I'm losing some of my x velocity. So 45 degrees is the max range. Okay, that's the max. Okay. Now let's look at what happens here. Let's say I launch at 60 degrees. Okay, if I launch at 60 degrees, the object flies up, okay, and lands somewhere here. Okay, and this is 60. Now, if I were to launch at 30, okay, again, I'm going to decrease the amount of time that I'm in the air, but have more x velocity. So if I launch here, then my projectile will fall and hit right at the same place. Okay, so if I have complementary angles, then they will strike at the same position. But 45 degrees will give me my max range for a projectile.